Okay, have you all gone through a proper microcontroller course before? Yes, right? Huh? No, serious? Okay, usually we cover, microcontrollers in a programming course, which I believe you all have gone through. Yeah, so what I'll do here is that, because you're going to use it for the design in Lab 2, I'll go through, what are the use cases, so that it give you some ideas how to use some of these features that you have in a microcontroller. Okay, so we also cover the different types of peripherals. What are peripherals? Okay, unlike microprocessors, microprocessor only have arithmetic and logic unit. All right, so for microcontroller, we have peripherals like ADC, DACs. We have general purpose I/O. Okay, you can use it to control your motors. Right. Then we also have communication ports. All these are the peripherals. Okay, we'll go through how to configure some of these peripherals, and I'll provide one use case so that you have some ideas how you can make use of microcontroller. And finally, we'll conclude with a selection of microcontrollers. Okay, so this is a block diagram of what a microcontroller looks like. Okay, essentially, you have things like the main processor. So in a micro P, you only have this guy. Okay, so your ALU, everything is all here. Right? For microcontroller, it connects you to your ROM, which you can use to store your program. You can also use it to store, configuration data. Okay, and of course you can use it to store RAM, where you can do intermediate calculation. Then all these things can be done in the RAM. All your variables can be stored in the RAM. Okay, there can be extension to your external bus. All right. So if let's say you do not have enough memory on board, this shaded block are things that is on board the microcontroller. So if there's not enough, some microcontroller allows you to extend the memory. Let's say you want to design something to monitor temperature in the ocean, and this sensor, you just drop it there for one whole year. So you're not going to pull it out, right? So you may need additional memory. Okay, so you can put all these things in. And of course, you have all these peripheral, which are all the I/O devices that you can have. Okay, so this whole thing are all peripherals. Okay, so what are the type of peripherals that you can have on a microcontroller? So this is still generic. I'm not referring to any particular microcontroller. So there are GPIO. So this GPIO can be configured for either input or output. They can be digital. They can also be analog. Okay. Okay. The other thing is communication. Okay. Unlike a microprocessor, microcontroller comes with configurable communication port. So this port, you can either configure it as a UART. So UART is our standard interface, the RS-232. Okay, or you can have Ethernet. You can also have USB, as well as I2C and CAN. Okay, I2C and CAN are bus protocol. Later I'll show you what is the difference between a bus protocol and direct communication. Okay, SPI is a serial interface, but it is much faster than your UART. Okay. Then we also have timer. Okay, what do we use the timer for in the microcontroller? Sometimes you need to measure time. Okay, so the timer can be used. Let's say for example, you want to set up a PWM signal. You can make use of the timer to set up the output frequency for your PWM. Okay. Sometimes you need to measure events. Right? Let's say you activate, a sensor, and then you need to read back when the sensor has, completed certain data collection. So timer can be used to count the interval, that is required to collect your data. Okay, other things are like analog to digital converters and digital to analog. So this one, because your microcontroller is operating everything in the digital domain, so you need to have this converter in order for you to talk to the outside world. And if you are using things like encoders, digital encoders for motors, then this quadrature encoder allows you to read directly from your digital encoders. Okay, and of course the pulse width modulators that we use, to control, let's say, your DC motor drive. Okay, and then external memory is what we use in order for us to extend the amount of memory that we have. Okay, so this is a typical form of I/O in a microcontroller. So you can have digital pin, all right? So this digital pin allows you to either read digital signal or it allows you to write digital signal, okay? So this one refers to external DACs or ADCs. External meaning that it has already converted everything to digital form. So you can connect it to your digital I/O port, okay? If you're talking about the internal one, right, then the analog signal goes in directly, okay? And for all microcontroller, inevitably you need to talk to some external devices. Right, so later I'll show you an example of some of this communication that we have. And when we talk about configuring, right, because all this peripheral on your microcontroller, it's up to you to decide, whether you want to use it as an input pin or you want to use it as an output pin. Okay? So you need to write to a register. So let me show you what I mean by this. Okay? So let's say, for example, I want to use pin 16 and 17 on my microcontroller. So here I need to tell the microcontroller, what is the purpose of these two pins. Okay, so this is a configuration part when I put in pin mode. Okay, so I'm telling the compiler to insert all this configuration so that this TRIG pin is configured as an output. That means I can write information to it, and then the other pin I configure as an input. Okay, and you can reverse the pin itself, right? Not necessary that it must always be like this, So it's up to you to define. Okay, then you have control registers, and okay, so these control registers again will determine how your peripheral actually functions. Okay, and we have status register. This is internal to the microcontroller. So status registers can be used to read things like flags. So if you have a analog to digital converter, you will be able to read the flag so that when the conversion is completed, then you read the information. Okay. What other thing? You have data registers that can be used to hold things like, let's say you have a timer. You want it to count to a certain value. Okay. So this will be stored in your data registers. Okay, this one this is an example of some of the use case for microcontrollers. For handheld devices, all right? So some of you are wearing smart watches. Okay, so this definitely have microcontroller in them. Then your portable GPS as well as your programmable calculators. So all this will have microcontrollers in them. Okay, so these are examples of some of the so-called ports that you can connect. Okay, I'll go through this use case. For your lab 1, okay, you'll be doing only this part, right? The motor and the ESC. Okay, we will not put in the propeller, okay, so that people don't accidentally injure somebody. Okay, so this example, the main microcontroller is this guy. Okay, this is what we call the flight controller. Okay, and as I mentioned earlier, right, there are COM port. So this main microcontroller, this is the one that will talk to the other microcontrollers. So all these ESCs, they also have a small microcontroller in them, correct? Because when you talk about the brushless motor, right, you need to have some commutation logic in there, okay? So this commutation logic are actually implemented inside here, okay? And the main guy here, all right, the one who is flying the drone, will tell all this ESC how much power it needs, so that you can fly a particular trajectory. Now, besides controlling the actuators, okay, this guy also needs to read information from the sensors. So one of the sensors that drone needs is position. So position can come from things like GPS. Okay. If you are flying indoor, no GPS, what we do is that we can also have UWB. Okay, UWB is a ultra-wideband beacon that can provide you with very accurate positioning. Okay, and then if you want to do things like observation, right, then you may want to have a camera. So this camera can go onto a gimbal so that you stabilize the image. Okay, and all these things are all done by one main microcontroller. Okay, and I didn't bring my drone, but okay, one of these popular ones is the STM32F, 401 or 407. All right, and of course for a drone you have receiver. Again, receiver has a microcontroller in there. Okay, and what else? Did I miss anything? I think basically, okay. So these are all the different parts that you have. This one is the flight battery, and of course you have a safety for the whole thing using a remote controller. Okay, how do we select the microcontroller? Well, you'll find that for all microcontrollers, the number of pins that you can use for your application is limited. So there will be a finite number of digital pins, finite number of analog pins. Okay, so you must make sure for the application that you have, the number of I/O pins that you require, right, can be provided by that microcontroller. Okay, and then the interface. What kind of interface do you need? Do you need analog? Do you need digital? Do you need PWM? Okay, so like the picture I showed you earlier, for the main microcontroller to talk to the ESC, right, they actually use PWM. Okay, they don't use the communication protocol, right? But if you are talking to GPS, then you need the communication protocol. Okay. Right. Then for memory, let's say for flight control, you need to store a mission. So you must make sure that whatever memory that you have, right, is enough. Okay. And sometimes, let's say for those that I'm used to working with, right, I also need to store all the flight control information. It's like the black box on the commercial aircraft. So for drones, if I fly, I make sure I have a black box in there also. So if something happens, at least I can do some forensic to determine what went wrong. Okay? So you must make sure this microcontroller that you have, right, can support the external data storage as well. Okay, and then depending on the complexity of your program code, the internal RAM must be able to provide sufficient storage. Okay, then right, for different application, you may also require to have interrupts. Right? If you try to use things like polling, what's the difference between polling and interrupts? Polling, basically, you need a microprocessor to go and check. Okay? So if I'm going to poll you guys, right, that means I'll check, are you okay, are you okay, are you okay? Then you reply to me. Correct? Okay, that's polling. Okay, got question, that's polling. Okay, but what's interrupt? When you just talk, okay? Okay, some interrupt are good, you raise your hand, then you ask a question. But some interrupts not so good, because you just talk. Okay, all right, so same microprocessors, okay? Depending on your application, then you will decide whether you want to use interrupts or you want to use polling. Okay, so you can actually disable all the interrupt on your microcontroller, and then you just use polling. Okay. Okay, then you also need to consider the processing speed. right? So different microcontrollers run at different speed, right? Some are only in terms of like, Arduino is how fast? Only 10 megahertz, okay? So if you go for things like the STM32, this can go at 1 gigahertz. Okay, so the speed also very different. But of course, cannot compare with your handphone or your laptop, lah. Right? Those are super fast. Okay, so without further ado, let me go into the Arduino. Okay, so for Arduino, you'll find that it has all the interface that you are looking for, right? Whether digital or analog. Okay, and you also have things like PWM signals. Okay, so instead of going through all these things, right, let me go through the board first. Okay, so this is the board that you'll be using for Lab 2. Okay, and the board are basically, putting in maybe additional things like all these connectors, right? The main thing, the Arduino, is this guy here, right? And you put in some LEDs for you to know what is the status of your program. So you can program the LED to flash or to do certain things, so that you know what's going on, okay? And they group the so-called pins into different groups, right? So let's say, for example, this group labeled 5, right? These are all the analog pins in your Arduino, okay? And then 4 are all the digital pins, okay? Can you program the Arduino analog pin to do digital function? Yeah, okay. Same, digital pin, can you do for analog? Can you program digital pin to do analog? Cannot, okay? But analog pin, you can use it to program for digital. Okay, why is it that you cannot? Okay, the digital pin doesn't have ADCs and DACs. Okay, so that's why for digital pin, you cannot program them to do analog function. But for analog pins, we can use it to, program it to give voltage high, voltage low. And that will be the same as your digital pin. Okay, but the internal structure is slightly different between digital and analog pins. Okay, 6 is all your power group, right? So you have 3.3 volt, you have 5 volts, and you have ground. Okay, and they also allow you to pipe external supply into the board, which we normally don't use. Okay, so you want to use power supply, right? You go through this power jack, because this one is really designed for power input. Okay, and you have a USB port here, right? And then some switches that you can use. And the reset is also pulled out here. Okay, so my mistake, the Arduino is 16 megahertz, not 10. Okay, so for the programming of Arduino, there are 5 steps that you need to remember. Okay, so the first thing is actually the program. Okay, so the program basically has 3 parts, right? So the first part is the declaration of variable. The second is the initialization, and the third part is the code that you put in to control the Arduino. Okay, so I show you the example of so the top, right, is the declaration of all the variable, which is here, right? So we use float for all this, then there's a character, and then we have string declaration. Okay, now besides the declaration of the variable, right, we also provide compiler directive. Compiler directive basically tells the compiler, what to do. Okay, so here we tell the compiler that we are using this library. Okay, all the .h are the library files. Okay, so we just lump everything under declaration of variable. But on top of that, you can also specify compiler directive. So you can also tell the compiler that, okay, whenever I use this, TRIG, right, treat it as the number 16. Okay? These are all compiler directives, right? So these are actually the declaration of variables. Okay, so this is the first part. The second part is the initialization, right, or the setup. Okay, so this is the second big chunk, right? So this part here is lumped under here. Okay, so I have a setup function, and here's where I set up whatever peripherals that I have. Okay, so in this case, I have a I2C display. Okay, so I'll just call the library for the I2C display in order for me to set up this display to provide the information that I can read from the display. Okay, and if I want to sort of like configure the pin, right, this is also where I will set up my pins. Okay, okay. So this is the setup part, and then the third part is the main loop. Okay, so all Arduino has all three parts. Okay, so the main loop is where you put your program to do a certain function. Okay, whether to read, from a sensor or to output a command to your actuator. Okay, so these are actually things that you need to do, in order for you to complete your task. Okay, so for Arduino, all the sketch or the program, they call the program the sketch, have an extension of .ino. Okay, and okay, and whatever you need to do, right, basically is all provided in the IDE. Okay. Okay, so for Sketch, unlike other C program, you can put your program anywhere, right? So if you use Linux, you just type GCC, then the name of your program, and you do the compilation. Okay, but for Arduino IDE, all the program that you have, right, must be in a separate directory. Right? The directory name will be the same as your program name. Okay, another thing, for this Arduino IDE, it supports many different types of boards. So in case you all have not used, okay, I have used it for things like even, the DJI drone. Right? They actually has an Arduino board that you can, attach to the top of the drone, and that board can be programmed. So all you need to do, right, is that you need to install the library for the different board, and then when you connect the board, you need to go to Tool, and you need to select. Okay, so even for Arduino itself, right, there are many versions of Arduino. The one that you are using will be the Uno. Okay, and there are also some like a $2 board. I think it's Arduino Micro or something. Okay, so if you are using a different board, then you will need to tell this IDE the pin configuration that you are using. Okay, so the IDE actually makes a lot of things easy for you. Okay. Okay, so in order for you to run programs and all this one is to compile. Okay, so you see it's compiling. And if there's no error, right, then you can just click this button to upload. You can see there's an upload whenever I overlay there. Okay, so basically these are all that you need to do in order for you to make use of the Arduino. Question? So basically for Lab 2, these are the main things that you need to look out for. And of course, when you design your experiment, it's up to you which pin you want to use. So no two groups should have exactly the same pins. Okay, so these are some of the basic functions that you can make use of in the Arduino. So I won't go through in detail because all this already speak for itself. Okay. 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 One thing to note is that you can actually, you know, write debugging codes in your Arduino, and then read back the information using this serial print. Okay. This serial begin is something that you put in the setup, and then the serial print. Okay. These two commands are things that you can use to send back, to the IDE so that you know what is going on. Okay, so here, you just need to click this, okay? Then a monitor will come out, and when you run your program, right? Okay, now it doesn't come up because I don't have a board attached. Okay, so when you run your program, all right, whatever you print, in your program, it will come out in the serial monitor. Okay? So this code doesn't run because I purposely have some errors in there. Okay. Okay. Anyway, you'll get a copy of that code in lab 2. Okay. All right, so I've gone through all the microcontroller. Any question on that? Oh, okay. Okay, so next thing will be the serial communication interface. As I mentioned earlier, there are different types of serial communication on the microcontroller. Okay, so RS-232 and UART are basically serial interface. Okay, and this only support one device. So if you use this interface, I configure a pin for either UART or RS-232 kind of communication. You can only connect to one device. Okay, the I2C bus you can connect to multiple devices. Okay, similarly, SPI also can be configured to many devices. Okay, so I'll go through some of this. Okay, so first of all, RS-232. This one has been around for many years. So in the RS-232, we have data line, and then we have handshaking control. We also have timing. Okay, so UART and RS-232, these are the slowest communication. Okay, all right. So for RS-232, you'll find that there are altogether something like 20 over pins that are defined, right? But not all of them are used. Okay, and for high-speed communication, right, we have a standard called RS-45 that will allow us to go longer distance, at the same time increase the speed of the communication. And for this kind of serial interface, right, the communication speed is what we call baud rate. Okay, so by, the standard baud rate for this UART, right, is 9,600 bits per second. So it's 9.6 kilobits per second. But it can go up to 100 kilobits per second. Okay, and then with RS-45 standard, you can actually go up to about 1 kilometer in terms of distance. Okay, and this is useful if let's say you need to do hardware-in-the-loop simulation, and the equipment that you have, right, can be like maybe you're controlling some very high power system like an engine. So you want to house it in a special area, right? Then the control room is at another location. Then you need this kind of long distance communication. Okay, so these are the pins, right? The 25 pins that that's defined for RS-232. Okay, but not all are used. Right, so the one that we use, right, is pin 3, which is the receive. Okay, no, sorry, pin 2, which is transmit, pin 3, receive. Okay, and one more, which is the signal ground, pin 7. Right, the rest ready to transmit, and all these things we don't really use. Right, these are actually defined in the good old days, where we have all these mainframe computers. Okay, so mainframe computer will use all this in order for them to do the communication. But in today's context, we just need 3 pins. Okay, transmit, receive, and signal ground. Okay, so even if you have 25 pins, right, we just use 3 of the lines only. Okay, which is pin 2, pin 3, and pin 7. Okay, the other way is to make use of all this ready to transmit and all these things. But for all the application that we have using microcontrollers, we don't use the one on the right. We always use the one on the left. Okay. Okay. So RS-232, UART, these are same standard. Okay, low speed communication, and these are also quite short range. Okay, if you want to use, let's say, bus communication, then we can actually use only 2 lines. Okay, but we can talk to up to 127 devices. Okay, so how does bus communication work? Okay, basically there are 2 signals that is required. One is the clock signal, and the other one is the data line. Okay, as you can see here. Okay, SCL is a clock. So the clock basically just provide, the so-called clocking. Let's say this one is SCL. This one is a regular pulse. Okay, and then you have the data line. Okay, the data line provides the data that you want to transmit across. Okay, so let's say, for example, yours is triggered on the downward edge. Then here you read a 1, here you read a 1, here you read a 0. Okay, so this will be 1, 1, 0, and so on. Okay, now how does this work? Okay, so you can have multiple devices. Right? These are all the slave devices. So at any one time, any one of them can become a master. Okay, right? So if anybody wants to talk, okay, what they do here is that they will pull this SDA low. Okay, right? So the master is the one that will provide the clock signal, but any one of them, if they want to talk, they just need to pull this SDA low. Okay, this is the data line. So once you pull it low, right, the rest of them will, all these other devices will detect that this line is low, and all of them will start to listen. So the first information that you put onto the data bus will be the address of the party that you want to send the information to. Okay, right? So you put out the address, and then whichever slave which has this address will have to start clocking in the information. Okay, so as we have mentioned, right? Okay, so all the slaves will have an address from 0 to what? 127. Okay? Correct. So there are 127 nodes. Okay, so you cannot put 0. You have to put 1. Why? You put 0, they also don't know why it's 0, because you have to put the line low first, right? Then everybody start listening. Okay? So you have to put it low for 2 cycles, then everybody start to listen. Okay? Then you need to put a valid address. So this address can be from 1 to 127. Okay? So if let's say the address that you put out is 067, right? Then the device with 067 knows that the information is for them. Okay? And following that, you can pass in the data that you want to send. Okay. Now, for I2C bus, right, all the manufacturers already agreed beforehand. Let's say if I'm producing a display for the I2C, then all the display will have a certain address, like 67 or another. Usually they will have 2 addresses reserved for each type of devices. Okay, so I can have, let's say, 2 display. One is 067, the other one is 071 or something. Okay, so I can actually send separate information to the 2 different devices. All right. Okay, so this is how I2C will work. So we can connect up to 127 of them, and the clocking speed is limited to, again, 100 kilobits per second. Okay. Okay, what else? I already mentioned SCR, SDA. Okay. Okay, so during transmission, the first byte will include the 7-bit address. Okay, so you put in the address, then you put in the actual data. Okay, so this thing operates on 3.3 volt. And if you want to have 5 volts, you need to have a level converter for these 2 signals. Okay, so just be careful, right? Whichever device that you connect to, right, must be accepting 3.3 volts logic. Right? So if you put in a 5 volt, then you must have a logic level converter. Okay, again, the distance for I2C is only limited to a few meters. Okay, what else do I need to say about this? Okay. For all these devices where you have a bus, why is it active low logic? Is that you do not know beforehand, all right, how many devices we are going to connect. Okay, so usually the output stage of all these bus are open collector. You need to connect pull-up resistors. All right, so that's why when nobody is using, right, the output will be a 1. Only when you need to put information, then the output becomes a 0. So if the bus is left unconnected, it will not create havoc because the output is always a 1, okay, or floating. Okay, the other type of device that we have is the SPI. SPI is a serial interface, but it provides full duplex operation. Okay, I2C, can it provide full duplex? What is full duplex? Both can talk and listen at the same time, right? What about I2C? Can you do a full duplex? Cannot, right? Because we only have one data line. Okay, so that data line, only one device can talk. Okay, or the rest are all listening. Correct? So it's a half duplex for I2C. But for SPI, we can do full duplex. And how is this done? We have a clock signal, all right? And then we have, MOSI and MISO. So one is input, one is output. Okay? So you can actually, these 2 are the data line, all right? These 2 are data line, this is a clock. Okay? And we have a chip select. So if you have one device, the master needs to provide 4 lines in order for us to talk to one device. If you have 2 devices, then the master needs to have a separate chip select for the second device. So for 2 devices, you need 5 lines. Okay? For 3 devices, you add 1 more. Okay? So you need 6 lines. Whereas the clock, these 2 input and output signal can be shared for all the devices. Okay? And how you talk, so for this one, the master will decide, okay, who should be the one talking. Okay? So if the device is not selected, then it cannot put any information onto the input and output buses. Right? Okay, so what can you say about this when it comes to communication? What kind of configuration can you have for this? Okay, unlike the I2C, right? I2C, anybody can put information on the bus, I don't have to wait. The master what the master does is only provide the clock signal, right? The rest of them, they can put information anytime they want. Correct? But for this, it's different. The master is the one that controls who can talk, right? So for this kind of connection, you can only have a centralized control, okay? So if the centralized controller goes dead, then everything is dead, okay? But for I2C, you can actually tie the clock signal, to a clock generator. You don't even need a master, okay? So for that one, there's no master, so everybody can make use of the data bus. So for I2C, you can do, distributed type of network structure, okay? You can, of course, you can also do centralized. But for this one, you can only do centralized. You can't do other types of network structure, okay? And the disadvantage, if this one goes down, that's it, okay? But if you need very fast communication and you need two-way communication, simultaneous two-way communication, then SPI is the way to go, okay? And SPI is faster than I2C. Okay, so so basically, the number of SPI devices that you can connect is limited by the number of pins that you have on your microcontroller for you to do the chip select. Okay. So for the application in drones, right? Usually, I only have my GPS on SPI. The rest of my system are either on PWM or on I2C. Okay. So I2C 127 devices, right? So I can do a lot of things. Okay, UART we mentioned earlier, right? So UART can do full duplex, okay? But one communication port can only communicate to one device. Okay? So this guy, if you have two devices, right, then you need 6 pins, right? SPI, 6 pin, I can control 3 devices. Okay? And for I2C, I need three lines, right? SDA, SCL, and ground. Okay? So here I haven't shown the ground. Oh, here this one got ground. Okay. Okay? The SPI I haven't shown the ground here. But just remember, you need to have ground for all of them. Okay, so this one I haven't shown. So you actually need one more line for the ground. Okay? All right, so for this is standard serial interface. And again, the maximum speed that we can go now, right, is about 100 kilobits per second, right? 115.2 kilobits.